Welcome to this problem walkthrough on LeetCode problem number 1383, Maximum Performance of a Team. In this session, we'll explore the problem requirements, discuss possible approaches, and work toward an optimal solution. Let's dive in. In this problem, we are tasked with forming a team of engineers to maximize their performance. We are provided with two integers, n and k, as well as two arrays speed and efficiency, both of length n. Here, n represents the total number of engineers, and k is the maximum number of engineers allowed in the team. Each engineer has two attributes, their speed and efficiency. The speed, I, array specifies the speed of the ith engineer, while the efficiency, I, array gives their efficiency. The goal is to form a team of up to k engineers such that the team's performance, which is calculated as the product of the sum of their speeds and the minimum efficiency among them, is maximized. Lastly, since the result can be very large, we need to return the maximum performance modulo 10(9 plus 7. Now, let's look at the constraints and the output format. The efficiency of each engineer lies between 1 and 10(8, while their speed values range from 1 to 10(5. The size of the team, k, can be any value between 1 and n, where n itself can be as large as 10(5. The output of the problem is a single integer, which represents the maximum performance that can be achieved, modulo 10(9 plus 7. To better understand the problem, we'll explore some examples. In the first example, we are given n equals 6, speed equals 2, 10, 3, 1, 5, 8, efficiency equals 5, 4, 3, 9, 7, 2, and k equals 2. Here, the maximum team performance is achieved by selecting the engineers with indices 2, 5. These engineers have speeds of 10 and 5, giving a total speed of 15. Their efficiencies are 4 and 7, so the minimum efficiency is 4. The performance of the team is the product of the total speed and the minimum efficiency, which is 15*4 equals 60. Therefore, the output for this example is 60. In the second example, the values remain the same for n, speed, and efficiency, but now k equals 3, which means we can include up to 3 engineers. The optimal team in this case consists of the engineers with indices 1, 5, 4. The total speed of these engineers is 2 plus 5 plus 1 equals 8, and their minimum efficiency is min, 9, 7, 5 equals 5. Multiplying these values, the team's performance becomes 8*5 equals 40. As a result, the output for this example is 40. In the third example, we have n equals 3, speed equals 2, 8, 2, efficiency equals 2, 7, 1, and k equals 2. Here, the best team consists of the engineers with indices 2, 3. The sum of their speeds is 8 plus 2 equals 10, and the minimum efficiency is min, 7, 1, equals 1. However, since we consider the product of the total speed and the minimum efficiency, the performance of the team becomes 10*7 equals 70. Thus, the output for this example is 70. Additionally, the constraints for this problem push us to find an efficient solution, as the values for n, speed, and efficiency can be quite large. Lastly, we should also consider special cases when designing our solution. For example, what happens when multiple engineers have the same efficiency but different speeds, or vice versa? Other edge cases include scenarios like having the smallest possible team size, or k equals 1, or the largest possible team size, or k equals n. It's also important to think about situations where all engineers have identical speed or efficiency values. Handling these cases correctly will ensure that our solution is robust and performs well even for the upper limits of the constraints. To solve this problem, we first consider the brute force approach. The idea here is to generate all possible combinations of engineers, with subsets of size up to k, and calculate the performance for each subset. For each subset, the performance is determined by multiplying the sum of the engineer's speeds with the minimum efficiency in the subset. While this method is straightforward, generating all subsets is computationally expensive since there are 2 to the power of n subsets to consider. On top of that, for every subset, we need to compute the sum of speeds and find the minimum efficiency, which adds an extra cost. This results in an overall time complexity of 2 to the power of n*n. While this approach is simple to conceptualize and implement, it becomes impractical for larger values of n, such as when n exceeds 20, as the computation time grows exponentially. This makes it unsuitable for solving the problem within competitive programming constraints. To address the inefficiency of the brute force approach, we turn to an optimized method that combines sorting, a greedy strategy, and the use of a priority queue or min-heap. In this approach, the first step is to sort all engineers by their efficiency in descending order. This is crucial because the overall performance of a team is constrained by the lowest efficiency in the group. By sorting, we ensure that as we iterate through the engineers, the current efficiency is always the smallest in the subset we are considering. Next, we use a min-heap to manage the k largest speeds. This allows us to maintain the constraint of having no more than k engineers in the team. If the heap grows beyond size k, we remove the smallest speed to keep the team size valid. As we process each engineer, we add their speed to the heap and calculate the performance as the product of the current sum of speeds and the current efficiency. By keeping track of the maximum performance encountered, we ensure the solution is optimal. This strategy is efficient because sorting simplifies the problem structure, the heap manages the top speeds dynamically, and the greedy method ensures we make the best choice at each step. Now let's analyze the complexity of this approach. Sorting the engineers by their efficiency takes O, n log n. Iterating through the engineers and maintaining the heap has a complexity of O, n log k, where k is the maximum team size. Combining these, the overall complexity is O, n log n plus n log k, which is efficient and suitable for large inputs, even when n is as large as 10 to the power of 5. Of course, this method requires additional space for the heap, but this trade-off is acceptable in most scenarios given the significant reduction in computational time. This efficiency makes the approach ideal for competitive programming tasks, where both time and space constraints are critical. The optimized approach using sorting and a min-heap emerges as the best strategy for this problem. Its O, n log n, time complexity ensures that it scales effectively for large inputs, while the greedy nature of the solution guarantees optimal results. A key insight here is recognizing that sorting the engineers by efficiency simplifies the problem, as it allows us to maintain a valid team dynamically using a heap. This drastically reduces the complexity compared to the brute force method, which is infeasible due to its exponential time requirement. By weighing the trade-offs, we can confidently conclude that this approach is both practical and optimal, addressing all constraints efficiently without requiring further refinements. To solve this problem, we need to maximize the performance of a team that can include at most k engineers. The performance is calculated as the product of the sum of the speeds of the chosen engineers and the minimum efficiency among them. The key challenge here is that both the speed and efficiency factors influence the performance, and we must ensure that the team respects the size constraint of k. The first step in our algorithm is to sort the engineers by their efficiency in descending order. This is crucial because the performance depends on the minimum efficiency in the team. By iterating through engineers in this order, we ensure that each engineer's efficiency becomes the threshold for the team we are currently building. To achieve this, we pair each engineer's efficiency and speed into tuples, and then sort the list of tuples with efficiency as the primary key in descending order. This allows us to process the engineers in the correct order for our calculations. Now that the engineers are sorted by efficiency, we need a way to manage the sum of the speeds of the team members efficiently. This is where a min-heap comes in. A min-heap is ideal because it allows us to efficiently remove the smallest speed when the team size exceeds k. This ensures that we always maintain the top k speeds in the team. As we process each engineer, we add their speed to the heap and update the current _speed_ sum. If the heap size exceeds k, we remove the smallest speed from the heap, which reduces the current _speed_ sum accordingly. At this point, we calculate the performance for the current team by multiplying the current _speed_ sum with the efficiency of the engineer we are processing. We also keep track of the maximum performance encountered so far. This process ensures that each possible team configuration, up to size k, is evaluated efficiently. The performance calculation is straightforward. We multiply the current _speed_ sum by the efficiency of the engineer currently being processed. After iterating through all the engineers, we return the highest performance value we encountered, modulo a given value, typically 10 to the power of 9 plus 7, to handle potential overflow. There are several insights that make this algorithm efficient. First, by sorting the engineers by efficiency, we ensure that the efficiency threshold for the team is fixed at each step, avoiding the need to recompute the minimum efficiency repeatedly. Second, using a min-heap allows us to maintain the sum of the top k speeds dynamically while adhering to the team size constraint. By combining these techniques, we simplify the problem into manageable steps that focus separately on efficiency and speed. To summarize, the core data structures used are a min-heap to manage the top k speeds efficiently and a sorted list of tuples to iterate through engineers based on efficiency. The time complexity of the algorithm is determined by two main factors: sorting the engineers, which takes O, n log n, and performing heap operations for each of the n engineers, which takes O, log k, per operation, resulting in O, n log k, for all engineers. Thus, the overall complexity is O, n log n plus n log k. The algorithm handles edge cases well, such as when k equals 1, where the highest performance is simply the maximum product of speed and efficiency, or when all efficiencies or speeds are equal, where other constraints naturally guide the solution. Even when n is less than k, the algorithm adapts seamlessly without exceeding the available engineers. This robustness and efficiency make it an optimal solution for the problem. This Python implementation solves the problem of maximizing the performance of a team. The input consists of n engineers, each with a given speed and efficiency, and a limit k on the number of engineers allowed in the team. The goal is to maximize the performance of the team, calculated as the product of the sum of the speeds and the minimum efficiency among the selected engineers. Explanation of the code. 1. Input preparation. The efficiency and speed arrays are combined into a list of tuples, and sorted in descending order based on efficiency. This ensures that we always consider higher efficiency engineers first, which is critical for maximizing performance. 2. Min-heap for speed maintenance. A min-heap, speed_heap, is used to maintain the top k speeds. The heap allows us to efficiently remove the smallest speed when the team size exceeds k. 3. Iterating over engineers. For each engineer, their speed is added to the heap and the total speed sum is updated. If the heap size exceeds k, the smallest speed is removed from the heap, and the speed sum is adjusted accordingly. This ensures the team size constraint is always satisfied. 4. Performance calculation. For each engineer added, the current performance is calculated as the product of the speed_sum and the engineer's efficiency, f. The maximum performance observed so far is updated. 5. A final result. The maximum performance is returned modulo 10⁻9 plus 7, as required by the problem constraints. This implementation effectively balances the team to maximize performance by prioritizing higher efficiency engineers while maintaining the top k speeds. The use of a heap ensures that the solution is efficient, with a time complexity of O, n log k. This is suitable for the problem's constraints, where n can be as large as 10 to the power of 5. Here, we begin by defining the max performance method, which takes in the number of engineers, their respective speed and efficiency arrays, and the maximum team size k. The first step is to pair each engineer's efficiency with their speed into a two-dimensional array. This allows us to process both attributes together. We then sort this array in descending order based on efficiency, since higher efficiency values are more impactful when determining the team's performance. Next, we initialize a min-heap, which will be used to keep track of the top k speeds. This allows us to efficiently remove the smallest speed whenever the team size exceeds the allowed limit. We also set up variables to store the running total of the selected speeds, the maximum performance encountered so far, and a constant mod to handle the large numbers resulting from calculations. If the size of the heap exceeds k, we remove the smallest speed from the heap, which helps maintain the team size constraint. After adjusting the heap, we compute the performance of the current team by multiplying the sum of the selected speeds with the current engineer's efficiency. This value is then compared with the current maximum performance, updating it if the new performance is higher. Finally, after iterating through all engineers, we return the maximum performance value modulo 10⁻9 plus 7 to ensure the result fits within the defined constraints. This approach ensures we consider all valid team configurations while maintaining optimal efficiency through the use of the heap and sorting mechanisms. In this example, we're working with 6 engineers, each having a specific speed and efficiency, and we want to form a team of at most 3 engineers to maximize performance. To solve this, we start by pairing each engineer's efficiency with their speed. Then, we sort these pairs in descending order of efficiency. This allows us to prioritize the most efficient engineers first, as efficiency acts as the limiting factor in the performance calculation. Next, we initialize three key variables: a min heap to keep track of the team's speeds, a variable to maintain the sum of these speeds, and another to store the maximum performance encountered so far. Now, we begin iterating over the sorted list of engineers. In the first iteration, we consider the engineer with efficiency 9 and speed 1. We add their speed to the heap, update the total speed sum, and calculate the performance as the product of this speed sum and the current efficiency. Since this is our first calculation, it becomes our maximum performance so far, which is 9. Next, we move to the engineer with efficiency 7 and speed 5. We add their speed to the heap and update the speed sum, bringing it to 6. The performance is then calculated as 6 multiplied by 7, giving us 42. This is higher than the previous maximum, so we update our maximum performance to 42. For the third engineer, with efficiency 5 and speed 2, we repeat this process. Adding their speed to the heap increases the speed sum to 8, and the performance becomes 8 multiplied by 5, which is 40. However, 42 remains the maximum performance. In the fourth iteration, we encounter efficiency 4 with speed 10. As we add this speed to the heap, we now exceed the limit of 3 engineers in the team. To address this, we remove the smallest speed from the heap, which is 1. After adjusting the heap and speed sum, the total speed becomes 17, and the performance is recalculated as 17 multiplied by 4, resulting in 68. This becomes the new maximum performance. Now, we consider the fifth engineer, with efficiency 3 and speed 3. Adding their speed to the heap increases its size again, so we remove the smallest speed, which is 2. After updating the heap, the speed sum becomes 18. The performance is calculated as 18 multiplied by 3, which equals 54. However, 68 remains the maximum performance. Finally, we look at the last engineer, who has efficiency 2 and speed 8. Adding this speed to the heap requires us to remove the smallest speed, which is 3. This adjustment brings the speed sum to 23, and the performance is computed as 23 multiplied by 2, giving us 46. Since 68 is still greater, it remains the maximum performance. At the end of the iterations, the final output for this example is 68, modulo 10 to the power of 9 plus 7, which is simply 68. In the second example, we have 4 engineers, and we aim to form a team of at most 2 engineers. We begin by pairing each engineer's efficiency and speed, then sorting these pairs in descending order of efficiency. This results in the list 5, 2, 3, 4, 2, 6, 1, 8. With the engineers sorted, we initialize the speed heap, speed sum, and maximum performance as before. Starting with the first engineer, who has efficiency 5 and speed 2, we add their speed to the heap and update the total speed sum to 2. The performance is then calculated as 2 multiplied by 5, which equals 10. Since this is our first calculation, it becomes the maximum performance so far. For the next engineer, with efficiency 3 and speed 4, we add their speed to the heap and update the speed sum to 6. The performance is then calculated as 6 multiplied by 3, resulting in 18. This is greater than the previous maximum, so we update our maximum performance to 18. Moving to the third engineer, with efficiency 2 and speed 6, we add their speed to the heap. Since the heap now contains more than 2 elements, we remove the smallest speed, which is 2. After adjusting the heap, the speed sum becomes 10. The performance is calculated as 10 multiplied by 2, which equals 20. This becomes the new maximum performance. Finally, we process the engineer with efficiency 1 and speed 8. After adding their speed to the heap and removing the smallest speed, which is 4, the speed sum becomes 14. The performance is calculated as 14 multiplied by 1, giving 14. However, the maximum performance remains 20. At the end of the iterations for this example, the maximum performance achieved is 20. Applying the modulo operation with 10 to the power of 9 plus 7 doesn't change the result, so the final output is 20. The time complexity of this solution can be understood by analyzing its core components. First, we sort the engineers based on their efficiency in descending order. Since sorting a list of n elements requires O, n*log n time, this is the complexity of the sorting step. Next, we iterate through the list of engineers, which involves a single loop running n times. During each iteration, we perform heap operations. Adding a new speed to the heap takes O log k, and if the heap exceeds size k, removing the smallest element also takes O log k. Together, these operations contribute O log k per iteration. Multiplying this by the n iterations in the loop gives us a time complexity of O n asterisk log k for the heap operations. This breakdown helps us understand how each step contributes to the overall complexity of the solution. Now, combining the time complexities of the sorting step and the iteration with heap operations, we get O n asterisk log n for the sorting and O n asterisk log k for the heap operations. Adding these together gives us a total time complexity of O n asterisk log n plus log k. In the worst case scenario, where k is close to n, log k becomes comparable to log n, and the complexity simplifies to O n asterisk log n. This shows that the sorting step dominates the overall time complexity, with the heap operations adding a smaller contribution. The space complexity of the solution can also be analyzed step by step. First, we consider the heap used to store the speeds of up to k engineers. This heap requires O, k, space. Next, the list of engineers, which stores n tuples of efficiency and speed, requires O, n, space. Finally, variables like speed underscore sum and max underscore performance are simple scalars, so they only use O, 1, space. When we combine these, the total space complexity becomes O, n plus k. However, since k is typically much smaller than n in practice, the space complexity is generally dominated by O, n. To better understand the efficiency of the optimized solution, let's compare it to a brute force or naive approach. A naive solution would involve generating all possible subsets of engineers, which results in 2 to the power of n subsets. For each subset, calculating the sum of speeds and finding the minimum efficiency takes O, n, time. This means the total time complexity for the brute force approach is O, 2 to the power of n asterisk n, which grows exponentially and becomes infeasible for large inputs. On the other hand, the optimized solution avoids this exponential growth by sorting the engineers and using a heap to maintain only the top k speeds, significantly improving efficiency. The optimized solution reduces the time complexity to O, n asterisk log n, by leveraging sorting and heap operations. By limiting the heap to k elements, we avoid the exponential complexity of generating subsets. In terms of best, average, and worst case scenarios, the time complexity remains O, n asterisk log n in all cases. For example, in the best case, if all engineers have the same efficiency, heap operations are minimal. In the average case, with random efficiency distributions, the heap operations are balanced. Even in the worst case, where efficiencies are in descending order, the heap operations are maximized, but the complexity still doesn't exceed O, n asterisk log n. The sorting step remains the dominant factor in the overall complexity, justifying the final time complexity of O, n asterisk log n. When solving this problem, there are a few common mistakes that can lead to incorrect results or inefficiencies. First, overlooking edge cases such as when the team size k is 1, when the number of engineers n equals k, or when all engineers have the same efficiency, can expose hidden assumptions in your logic. These scenarios need to be handled explicitly to avoid runtime errors or test case failures. Another mistake is sorting by the wrong attribute. Since the problem centers around maximizing performance, it's crucial to prioritize efficiency in the sorting step. Sorting by speed instead, for example, can fundamentally break the logic and lead to evaluating incorrect subsets. Finally, relying on brute force to generate all possible subsets of size up to k is highly inefficient. This approach can result in exponential time complexity, making it infeasible for larger inputs. Instead, leveraging optimized strategies like priority queues is essential to ensure the solution scales well. Another common pitfall involves the incorrect use of priority queues. Specifically, when maintaining a min heap of speeds, it's important to remove the smallest speed whenever the heap size exceeds k. Failing to do so means the heap no longer represents the top k speeds, leading to inaccurate calculations of the speed sum and, consequently, the overall performance. Additionally, integer overflow can be a concern when calculating performance, especially when working with large numbers. If the problem specifies modular arithmetic, such as mod 10 to the power of 9 plus 7, it's crucial to apply this correctly in all calculations. Ignoring this detail could result in incorrect results or runtime errors in programming languages with fixed integer sizes. By addressing these issues, you can avoid key mistakes and build a robust solution. From an interview perspective, it's important to focus on clarity and demonstrating your thought process. Start by explaining why sorting by efficiency and maintaining a sliding window of speeds, managed with a heap, is an optimal approach. Highlight the trade-offs between keeping the smallest speeds while maximizing efficiency, as this is central to the problem. Be ready to discuss the time complexity of the solution, typically O, n log k, where n is the number of engineers and k is the maximum team size. If you find yourself stuck during an interview, begin with a brute force solution and explain its limitations. Then, transition to optimized approaches using heaps or greedy strategies. It's also helpful to relate this problem to real-world scenarios, such as task scheduling, where similar trade-offs between efficiency and speed are often encountered. There are several related problems on LeetCode that help reinforce the concepts in this challenge. For example, LeetCode 23, Merge K-Sorted Lists, involves using heaps to efficiently manage the top K elements, much like this problem. LeetCode 253, Meeting Rooms 2, shares similarities in maintaining a heap to track overlapping intervals. LeetCode 621, Task Scheduler, focuses on balancing tasks and prioritizing efficiency, while LeetCode 857, Minimum Cost to Hire K Workers, employs a similar greedy and heap-based approach to optimize cost efficiency. When considering alternative approaches, brute force is one option. It evaluates all subsets of size k or less but is computationally expensive, with a time complexity of O(2 to the power of n). A more efficient method is the greedy approach, where you sort by efficiency and use a sliding window of speeds to evaluate the top k combinations. This approach has a time complexity of O(n log k), but requires careful heap management. Finally, dynamic programming is another option, exploring state transitions based on team size and available engineers. However, it is more complex to implement and may not scale as well as the greedy method in practice. Great job walking through this problem. We've covered the key concepts and techniques to solve maximum performance of a team. Remember to practice similar problems to strengthen your grasp of greedy algorithms and priority queues. Thanks for watching, and see you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!